Hi guys, it's Susanna. So those of you who know me know that there are a few things that I love more than growing heirloom tomatoes with my dad. And one of the best parts about this little quarantine situation for me has been I get to be around for the whole process, which has been really cool. Because the way you do that in New Hampshire is you start growing the plants in like under grow lights in the basement during March, and you put them in the ground right about now during May. So we're starting to get the plants ready to take them outside and put them in the ground, which is super exciting, but we're not there yet. So I'm in my basement and I have some lovely grow lights with lots of plants underneath them. I'm going to show you now. So here's a couple of tables of tomatoes. Those are heirloom tomatoes. I think we have 15 different varieties this year. And then over here, we have two more trays of basil and arugula mostly, and some peppers. So that's really fun. But that's not what I'm really here to talk about today. What I'm really here to talk about today is what we grow the plants in, which is soils. So those of you who know me will also know that I am super interested in soils and sustainable soil science. And so when I was thinking about doing this Earth History final project, I really wanted to do something about what Earth history can teach us about soils, and that brought me to the idea of carbon sequestration by soils. So if you don't know what that is, I'm going to use my basil plant because it's in a clear cup, so you can see like a cross section. So I'm going to use my little basil plant with the roots visible as my demo. I'll put that here for now. So if you don't know what soil carbon sequestration is, basically, it's the process by which carbon is introduced into the ground. So how does that happen? Well, I am sure you've all learned about photosynthesis during your science classes, right? So in photosynthesis, atmospheric carbon dioxide is taken in by plants and incorporated into the plant body, and the plant emits oxygen. So the process of carbon sequestration is the process by which that carbon that the plant takes in during photosynthesis is incorporated into the soils in which it lives. So the most direct way that happens is with the roots. As you can see with my little basil cross section here, the roots embody a lot of the soil. There's a lot, or basically the entire soil space in this little clear cup has roots in it. So all of the carbon that is taken into the plant, a lot of it goes into the roots, and when it goes into the roots, that carbon is incorporated into the soil. This happens both during the plant's life and after the plant dies. Its roots are already in the soil, so the carbon that's there just gets incorporated into the soil directly. Droppings from the top of the plant, like leaves and shoots, if one of these little leaves was going to die, it would fall into the soil where it would decompose, and the carbon that was in the leaf would be incorporated into the soil too. So that's one really big way that soil is able to take carbon from the atmosphere and put it into the soil. This process can be accelerated in a lot of different ways. For instance, a lot of microorganisms live in soils, like bacteria and fungi, and there are certain types of fungi that can do a nutrient exchange with the roots of plants. So the roots of plants will give the fungus some carbon in exchange for a limiting nutrient like phosphorus. So this is one of the many ways that soil transfer from the atmosphere to plants to soil can happen. So this is a really cool process, but there can also be soil losses. For instance, if there is groundwater leaching or if there's erosion and runoff, the carbon that's trapped in those soils can ultimately be lost and put back into the ecosystem that it was taken from. So it's a question of a net balance. If the input from photosynthesis and from soil microorganisms is greater than the soil losses, then soil carbon can build up over time. But if the soil losses are greater than the input from photosynthesis, then the soil is going to become depleted in carbon over time. So that's why this issue is really so important and gets talked about so much. If you can design a system where the net balance of carbon is such that plants are taking in more through photosynthesis and transmitting it into the soils and the ground than is being lost through erosion or microbe respiration or groundwater leaching or any other form of soil loss, you can build up soil carbon. And when that happens, you're essentially taking carbon out of the atmosphere, all the extra carbon dioxide that humans have put into the atmosphere, taking it out of the atmosphere, putting it in plants, and storing it in soils. So in this way, it's a strategy to reduce atmospheric carbon dioxide and to try to mitigate the impact of anthropogenic emissions. So laboratory tests have shown that this could potentially work for a couple of reasons. One is that plants have been shown to be able to grow bigger and be more productive in systems with more carbon dioxide. So that is, in a world like the one that we live in, where we're putting extra carbon dioxide into the atmosphere, in theory, plants should be able to grow bigger and perform better in that they're able to take more of that carbon dioxide out of the atmosphere and ultimately sequester it. For the purpose of this video, we're going to say that these tomato plants here, the big ones, are the plants that grow in a world with more carbon dioxide, while these ones over here, which are pretty tiny, grow in a world with less. The size difference in these plants really shows that these ones over here, the larger ones, have more leaf space and more capacity to take in more carbon dioxide, whereas these ones do not. So, because of that, these larger plants, which grew, in theory, in a world with more carbon dioxide, are able to grow larger and sequester more carbon dioxide than these smaller ones who grew in a depleted environment would be. Okay, so I took you guys outside for this part of it because I wanted to show you what a more natural ecosystem might look like. So do you remember that cup that I showed you? The little one with the basil in it? You could see all those roots that were growing in just that tiny cup with that tiny amount of soil. Now you can readily imagine what a tree like this, what its root system would look like, and how far it would spread, and how much of this soil would be covered with roots, or have roots inside of its cross-section. So, when humans began to dominate the world more and to get rid of ecosystems like this, they really reduced the capacity of global soils to hold carbon. When they switched from an ecosystem like this, with all these trees and all these plants and all this growth, to one like this, which was mostly grassy or agricultural or industrial, they really reduced the amount of roots in the soils. Without roots, the soils can't store carbons. And so because of that, there is today a really significant global carbon depletion. So the world's soils want more carbon. This makes it a really promising means through which carbon could be stored because there's so much of an excess space for carbon. Oh, hey, I didn't see you there. I was just thinking about soil carbon sequestration. So it seems really promising, right? You'd think it would be a really good way to capture the extra carbon dioxide in the atmosphere and store it somewhere. But there's a twist. Oh, I thought you were gonna do a twist. You'd think that this sounds like a great solution, but some recent research has shown that the laboratory studies don't always tell the whole story. So recently, some researchers from Penn State have examined some soil cores from Wyoming. These cores came from the Paleocene-Eocene Thermal Maximum, the warming event that's most commonly considered to be an analogy for modern warming. They were looking to see if carbon levels were elevated during this warming event, as carbon levels are expected to be during our warming event. What they found was pretty surprising. There was basically no organic carbon at all in these soils. So, what does this mean? Well, it could mean a lot of things. These soil cores from Wyoming represent one sample. There hasn't been a lot of other research from the P.E.T.M about this issue. These soil cores are also part of a fluvial basin. That means that the inputs and outputs were much more regular than they would be for other soils. This could impact the carbon levels. There are other ways that the carbon levels could have been impacted that were unique to that location. Overall, carbon sequestration could still respond in a similar way to how we expect it to. However, it could also mean something really different. It could mean that the increased temperatures or increased precipitation associated with a warming event like the P.E.T.M, or like our global warming that's anticipated to happen in the coming years, impacts the way that soil stores carbon. It could mean that it's much more difficult for carbon to persist in soils, and it's a lot easier for it to weather out. This could mean that what we're expecting to be a huge carbon sink in all of our terrestrial climate change models is actually a huge carbon emitter. This would have massive implications for how we model carbon emissions and climate change going forwards. So, more broadly, we don't really know what's going to happen with soil carbon sequestration. It could still be one of the most promising ways to curb anthropogenic climate change. Or
yes, okay. Keep going.
Or it could end up being one of the biggest emitters of carbon dioxide in a warming climate.
You gotta do
Either way,
okay.
soil will likely have a big impact on modern warming. What that impact will be, we just don't know yet. But what is the bigger lesson of this issue? The bigger lesson is that Earth history and the study of Earth history can have a much bigger impact on modern science than you usually think. Laboratory tests only told us. Anyway, back up the hill. I'm putting this in the video. Hey guys.
Is this all going in?
Yep.
Okay.
Laboratory tests only showed us that plants would get bigger with more carbon dioxide and be able to sequester more carbon. Only the study of Earth history was able to show us that this might not be true all the time. And because of this, we know that we shouldn't put all of our eggs in that basket. This just goes to show how important Earth history is today and to the study of modern anthropogenic climate change, baby.
You learn how to ride a bike.
Hi guys, thank you so much for watching my video. This is a little bit unrelated, but I did want to put it in, so I just put it after my last slide. I wanted to end back where I started with my plants in my basement, with a little personal plug for the viability and validity of sustainable soil science and sustainable agriculture, even though soil carbon sequestration and carbon farming might not be as important or as useful as it's often portrayed to be. Carbon farming and soil carbon sequestration is so interesting, and it's one of the most promoted reasons to practice sustainable farming. And it is a really cool and really interesting field of study, and I think it's really awesome that Earth history and geology are informing it in ways that laboratory sciences cannot, so that's awesome. But it's one of many, many reasons to think about and study and practice sustainable soil science. Sustainable soil science and effective land use and land management can prevent all kinds of other issues, including erosion and food availability and land management, and just a whole host of other sustainability and human rights related issues. It's a super interesting field of study, and I really hope that even though the viability of carbon farming is kind of being shown to maybe not be as big of a deal as we once thought it to be, that everybody still who is interested still looks into other really cool aspects of sustainable soil science and sustainable agriculture, because it's super, super interesting and super important. Yeah, but that's all. Thank you for watching. Me and my basil cup say have a good summer, and thank you for a great semester. Bye, everyone.
Get into it. Oh, I caught that on camera.